Okay, before I was rudely interrupted, so you smush the thing down, right? Maybe in the room or something. Keeping the, smush it down very slowly, take hours, okay? And then you release it, right? What happens? The temperature decreases, right? It expands. Okay? So that, what's going to happen to the pressure? Well, as the temperature is decreasing, it's going to go through the same, as it goes through the same set of volumes or some subset of the volumes, the temperature is always going to be less than it was when you did this, right? If the temperature is less, so is the pressure. Does that make sense? So you're going to get something like this. Okay? Now at some point that's going to stop depending on the situations. Like it might stop when you get back to room pressure, right? So maybe it stops here. Maybe for some reason it goes beyond, but in the usual case we're going to say, okay, it's going to stop here. So you let it expand back to original pressure. Now this is adiabatic. Okay? Now, the steepness of this curve depends on how the temperature changes. Okay? And that depends on characteristics of the gas. Okay, how much energy do you get out of a change in temperature? Well, the answer is, for monatomic gas, it's the same, doesn't depend on the gas. For a diatomic gas, it's the same, doesn't depend on the gas. But for a diatomic gas, it's not the same as for a monatomic gas. Why?
That's back to the more degrees of freedom, right?
Yeah, exactly. More degrees of freedom. Okay? Want to be more specifically about why there are more degrees of freedom in a diatomic?
Because you can rotate with the diatomic.
Yeah, because you've got two independent axes, and we discussed this pretty thoroughly. Yeah, it's been a month or more. But we discussed it pretty thoroughly, why that is. So I'm not going to go into the details of that, except to say, okay, you got the axis, and you're not going to get rotational energy about the axis through the two molecules, okay? Or the atoms. But any direction perpendicular to that, this direction, say, or this direction, you can have angular momentum, angular kinetic energy, independently about any two directions that you want to choose perpendicular to that axis, okay, at any instant. Of course, the direction of this axis is going to change from instant to instant because things tumbling and spinning and everything else. But relative to this axis, you still have two independent directions. And you think through the details of that. It can be a little confusing because it changes in position and that stuff. But, okay, so oh, you can walk in front of it. You won't break the camera. You never have. Okay. Okay, so, and this is key, but I got to keep going because we're almost out of time. So you're going to have to explain it to Elam. You have to be patient with him. But if you confuse him, he'll come back at you with multivariable calculus, and you're going to lose. So be careful. Okay, seriously. Why does the temperature drop? Because that's what happens when it expands. Well, yeah. Why? Well, why did the temperature rise when you compressed it? Or why does the temperature tend to rise when you compress?
You put energy into the system.
Again?
You put energy into the system?
Yeah, you're doing work on the system, okay? Well, when the thing expands, it's doing work. There's pressure on whatever's expanding, right? You're doing work against pressure. And remember, pressure is work per unit of volume, right? Okay, so the volume's changing, and it changes suddenly. What's going to do the work? It's the internal energy of the molecules. Okay? So we can make a note here. The work of the expansion at the expense of internal energy. Which is the kinetic energy of the particles. Make sense? Which gas does more work per unit of temperature change? Diatomic or monatomic? Diatomic, because it's got the rotational kinetic energy to expand, but that doesn't affect the temperature. The temperature is determined by how hard these molecules hit the walls of the container and each other and everything, okay? And that's translational kinetic energy. Rotational kinetic energy has no effect. You're as likely to be rotating into what you collide with as away from what you collide with. Sorry, okay? So only translational kinetic energy contributes to temperature. So if you change the temperature of a diatomic gas, there's more energy involved. Okay? Now, without going into detail, for an adiabatic expansion, PV to the gamma is constant. So if you know what the pressure and volume are here, you can figure out the rule for this curve. Okay?
Is that P times V to the gamma?
Yeah.
Or PV to the gamma?
You see any parentheses? What's directly to the left of the gamma? V. There's no implied parentheses in my world. Okay? And this is dictated by the fact that I had to type a lot of stuff and use typewriter notation. No implied division either. If it's divided by something, it's divided by whatever is directly follows the slash. And if I have more than one term in there, it's only the first term that's divided unless I've got parentheses, okay? Total, literal, order of operations. No exceptions, okay? Okay, so PV to the gamma is constant. And I've already told you what gamma is, okay? It's the ratio of specific heat at constant pressure to specific heat at constant volume, which for a monatomic gas is 5/3 and for a diatomic is 7/5. Okay? And you can reason out that if this exponent is 7/5, this curve is not as steep as if it's 5/3. And it's not as steep because you don't have as much temperature change. Okay? So I'll note it up here. But those are the reasons. Now, there's a little more detail, but it really just comes down to what I said. Okay, the fact that you get more work out of a diatomic gas for a given change in temperature than you do out of a monatomic. And it takes more work to change the temperature of a diatomic if you're trying to increase the temperature, okay? And that has an effect on the steepness of this curve, which of course depends on gamma. So you have just P equals some constant over V to the gamma, right? Where gamma is bigger than 1. So it's going to be somewhere between an isothermal, which is like a reciprocal first power, and a reciprocal second power, which is a lot steeper. Okay? Okay, so you do this. Now, the rest of a Carnot cycle, that we'll talk about more, is you do another isothermal. Okay? You now expand it isothermally, meaning you wait for winter day and you take the thing outside, okay? And you get the temperature down to whatever and then slowly expand it. Well, you take it outside where the temperature is, you wait for a day when the temperature is the same as it is after your adiabatic expansion. You get it out of the room, you don't want any temperature exchange, you take it outside where the temperature, where there's not going to be any heat exchange. And you wait till the temperature's just right to do all that, okay? Or, you know, otherwise arrange it. So now you have another isothermal. Didn't draw that very well, but you got another isothermal. And you follow that for a while. Okay? And you can work out what the temperature would be given circumstances. And then what? Okay, well, now you've allowed it to expand outside where it's cold. And then what do? You smush it down again, heating it up, and you immediately bring it inside, right? And since you haven't allowed any gas to escape, you're back to the original temperature, and you smush it down to the original volume, so it's going to have to be at the original pressure. So you got another adiabatic. Well, okay, so here's another adiabatic here. And you follow that curve back here, so you've done this. Now, have you had a net gain or loss? Okay. Here, you had to take heat away, right? Okay? Here, you had to put heat in. You put more heat in than you took away. So you have a net heat that goes into the system. Has the system done work?
Yeah.
Well, yeah. Here it did negative work. Here it did positive work. Here it did positive work, and here it did negative work, right? I'm sorry. Yeah, okay. Well, I kind of said that backwards, but there was work, there's work done, and the work turns out to be equal to the total area under the PV graph, because pressure is work per unit of volume. You have a net area under this curve, okay? So There's the work done by the gas. I think I have a sign wrong there somewhere, but you have the idea. Okay? So we'll take that into a little more detail. But that's the idea of a Carnot cycle. Okay? And this is a big deal. TH minus TC over TH. TH is the room temperature, the maximum temperature at which this thing operates in the example I gave, and TC is the outside temperature. Okay? This is the maximum possible efficiency for any closed process. This gives you the maximum possible ratio of work out to the heat you got to put in. If you know what the two operating temperatures are, you get that maximum possible ratio, and nothing else achieves that ratio. Nothing can exceed that ratio. Actually, the Stirling engine can theoretically achieve it. Okay? This is not a practical engine because it's slow because of the slowness of the isothermals. In no practical engine do you use isothermals. Okay? Although sometimes you come kind of close. So we'll talk a little bit more about the thermodynamics, but this is the essence of thermodynamics, and this is the second law of thermodynamics, which is right up there with Newton's laws. It governs the universe in many ways. Nothing can exceed this efficiency. Okay? So let's say
So TH is the maximum temperatural